Okay, OBS thinks we are connected. YouTube Studio thinks we are connected. This has got to be like take 47 or something. I swear, this today has been just one thing after another. Anyway, welcome back to Old School Coding, where today we are going to repeatedly try to talk to YouTube and repeatedly start the conversion of the 8228. Anyway, I am going to, just as a safety thing, just to verify things are actually working, I'm going to see if I can see this stream on my iPad, which is completely separate from anything that might be happening on the PC. And indeed, there it is. So now I'm going to go over here and say hello. And yes, we are in fact live, and chat is in fact live. Anyway, what I was saying before I was so rudely interrupted 15 bajillion times is our task for today is to implement the simulation for the 8228 system controller and bus driver. I did some work on a bit of code to measure timing of signals, and I was looking at displaying them, and then I realized that there are existing commercial off-the-shelf solutions for remote logic analysis. So you could have a project over there, and you have a logic analyzer hooked to it, and then you ship the data across the network, and you display it on your local system. So I'm going to be looking into seeing if I can find an open source or cheap commercial system for fetching data from across the net or from a CSV file or whatever and displaying it nicely so I don't have to write the display code myself. But with that in mind, I can't stop thinking about that. The timing, when we start getting multiple modules and we have timing relationships and one module does require timing from another, that's when I'll start hooking up the timing stuff. I already set those up and got them working, but I did not measure the timing of the 8224 yet. So 8228. I'm going to go over what the simulation is going to do. You'll see on the screen what the actual hardware does. If you want to read that, it does a little bit more. I'm going to do a little less. We are monitoring the data bus coming from the CPU and from the rest of the system. When the status strobe is strobed, we are going to snapshot the status bits coming from the CPU, and then we're going to make decisions on what kind of a cycle it is, mem read write, device read write, or interrupt acknowledge. And based on other signals, we will pulse these guys, I make them active at the right time and deactivate them at the right time. The timing, really simple. Status strobe hits. We will be driving the interrupt acknowledge, IO read, mem read cycles at that edge. The IO write and mem write is delayed. We'll have to remember that we need to do them. And when write goes active, we will assert those. We release the write control signals when write goes high. The read control signals get released on data bus in going low or hold acknowledge going high. So either one of those terminates the cycle for us. Down at the bottom, we have system bus enable. If it's low, we get to wiggle things. If it's high, we're locked out. So system bus enabled needs to be low for us to do our work. If it's high, we don't want to change the values of any of our output signals because somebody else is mucking with them. This is a shared control bus, by the way. If it's low, we get to muck with them, which means that it goes low. If it goes low while the control signal is supposed to be set, we need to set the control signal. So we need to have the ability for system bus enabled going low to check the logic on the rest of them and do the right thing, which means somewhere we have a little thing that says the output of this guy should be this value if system bus enable is low. Move that out of the way a bit and take it off of the OBS display. How am I going to do this? Well, I'm going to take the 8224 source and make it into 8228 source. First by filing off the serial numbers, and then starting to update things. Now I'm going to still refer to the PDF so I make sure I get wording right on most of this. This is called the System Controller and Bus Driver for the 8080A CPU. This module expects to see a status strobe, during which time the data bus contains status bits. Based on those status bits, on the latched value of those status bits, the output, the control signals are asserted at the correct time when enabled. Timing is similar to the 8228, but quantized. Okay, so come down here. If I look at this, we do have a name. Now, we need to see the data bus. Target.h defines for us the basic data types for the simulation, bit, byte, and word. I want to have a data type that represents the address bus and the data bus that looks, remember with the edges, we have edge, which is an array of 1, or a p edge, which is a pointer. So those look the same in source code. I want to have the same thing for an address bus and a data bus, where the guy that owns it has an array of 1 something, and the guy that uses it has a pointer to it. So this is a type def. Byte is a p data or a data sub 1. So the type called data is going to be an array of 1 byte, which will be a data word, a data byte. Okay. Now inside the CPU, it is likely that we will declare our registers to be of type data if they're 8-bit, and of type adder if they're 16-bit. So in a register pair, we don't actually store register pairs as a single storage. We have 2 bytes. Maybe I'll do some shenanigans with structures and unions, but maybe not. So far we're looking good. Nobody includes this header file yet, so the fact that it's got garbage in it is not important. So we need pdata, data, and that will be the thing we are using to sample the data bus. D is a bad name because there's a register called D. And I don't want to have the registers B, C, D reg, E, H, L, and so on. So B, C, D, E, H, L are all going to be reserved for CPU registers. So this is just data. We have some imported edges, and we have some edges we own. You can own an edge if you are the unique sender or the unique receiver. If you have multiple senders and multiple receivers, that edge has to be owned by some parent environment. Okay. And we do not have a state, well, we do have a status word, but the status word is a byte. Now, I may change that. I may store some bits or not. We'll see how that shakes out. So our inputs are ststb underscore dbin wr underscore hlda and bus enabled. Those are the pins that other people are going to send us. We may be the single, well, no, bus enable. I think we are maybe the single consumer of the bus enable signal. So I am going to make this the first signal we own. But certainly DBN, WR, and HLDA are owned by the CPU, and status strobe is owned by the 8228 or 24. So output signals, signals we own that are, this is input. Signals we own that are output are MEMR. They're all active low, MEMW, IOR, IOW, and int A. And we can go ahead and let the indenter indent that even though we're not compiling it yet. And I'm going to latch the status. I do need to have the layout of the 8080 status bits handy. I think I actually have them in another file. Let me see if I can find that. So let me see, do I have binary numeric literals available? That was a compiler extension back in the day. If so, no, okay, so I can't do copy paste. WSL is a little weird with copy paste. I'm used to the way X Windows does it properly. I'm used to the way Windows does it properly, and under WSL, neither of those work properly. Okay, so this is the header file that I used in a preliminary version of this that does allow me to say, here's the bits for these guys, and I did an octal version just in case I'm not allowed to use binary numeric literals. Now when I update that, it is building, which means we are cool. And I re-indent, and there we go. So instruction fetch, I've got to trim that off. Make it shorter. Yeah, the indenter is pretty consistent about its trailing comment columns. I think it's per block. But if I keep it shorter, it's easier. So what we're producing here is a set of masks that say if I have a status bit, if I have status word, here's how I peel out the bits. And here are the specific values of the status word as documented in the 8080 manual. And I've put in a reset value, which I think is the value of status that pretty much represents the reset state of the CPU. Anyway, that's what I will be setting my latch to, because that should be kind of a neutral, don't assert any of our outputs thing. Over on the right, I have laid out which of the signals are active so I can look at them. This helped me work out what the Boolean expression was for the outputs for the 8228. That will become important very shortly. So the rest of this is pretty much, doesn't change very much. I mean, I changed the names, but that's it. Verify the invariance, we need that. We need to initialize it, and it has a name. We've got a macro that will initialize it, and the name of the unit will be the name of the variable it's in. Shortcut. Finish initialization, and post, bist, and bench. Okay, there we go. Now, I could start with the 8224 source, which we're looking at now, and rip all the content out and put it back. But frankly, ain't got time to do all that ripping out and recoding. I think I'm going to start fresh. I8228.h, we're going to include that. And we're not yet building that file. So before we do, I want to grab all of these extern declarations, bring them over here, remove the word extern, then find the end of the declaration and go put in some braces. So this is now legal. It'll have warnings, but it's legal. We're going to take out the macro. Now we need names. So we call it CTL because it's a control chip. And if I'm not going to use a parameter, I will mark it void like this. And in this case, it's only unused because I haven't written it yet. So there's the to-do lines for that. And there's the re-indentation. I'm using the indent profile from 1991-ish. I looked back in my archives for that. Tuned up a little bit because some of the parameters changed since then. It's not exactly the same, but it's the same format. My Emacs configuration is similar to it, but there will be differences. So sometimes Emacs will indent things one way and indent will indent things the other way. As long as I indent it properly with the indent tool before I commit, that's good. But that's a habit I got into back in the late 80s working at Sun, where if your code didn't match the style properly, there were at least 2 higher level engineers that were just completely focused on that. Check out sometime why the indent man page has an option -BS, which stands for -Bill Shannon. Yeah, anyway. So there we go. Now we go into main.c. And anywhere we have 8224, we're going to duplicate the line and add an 8228 to it. So now we are actively doing stuff. I can get rid of that. I'm going to go in here and print top. So we can verify that we're actually getting into our power and self-test, built-in self-test, and benchmarking code. And yes, indeed, we are. So we're seeing that the output log differs from the expected value and that we're adding that we did the post, we're adding that we did the BIST, and we're adding that we did the bench. So we know we're getting to there. We know we're getting to there at the right times. I can remove these lines. Because frankly, while I set them up thinking I would be using them a lot, it turns out that I only use them enough to verify we're getting into them. So what do we want to do here? Well, let's see. Invariance of the control thing, assert CTL. Got to have a CTL. It's got a name, and the name is not blank. CTL init. I keep fumbling my fingers on this. I'm going to assert CTL and name are set, are provided like that. CTL, our name is the given name. We start initializing fields. CTL arrow data. Well, data has to be set by someone else, so data is going to be undefined until we get down to linked. The p edges are undefined until we get to links. So bus n. Well, that initializes with edge init. It needs a name, which is format %s:/bus n. and so on with all the other ones. These are all going to look the same, so what I will do is just grab that. There's two things I can do here. First of all, I could take all of these pointers and bring them into local variables and just operate on local variables. But I'm only going to do a couple things to each one. Well, I am going to do a couple things to each one, so let's do that. Also, this means that we will have a block of code that gathers this stuff up at the top, which we can just copy that block of code and delete unused variables later. So we're going to start off by setting the variables, and then we're going to edge init, and then we're going to explicitly set the value separately. So first block is find semicolon, trim to end. Find the blank, do that, and that is equal to CTL arrow signal, and this is a p edge, not an edge. Okay, so there's that. Now we want to set up our edge inits. Oh, but I don't need edge CTL. I don't need CTL in here. I just say edge init of bus n, and the name is format of %s colon bus n. Oh, almost messed up. Let's do the macro from scratch correctly. Find the semicolon, trim to end. Find the space, keep just that. Edge init of that, format of %s colon / that, trim the underbar. And then I'm going to say edge. Bus n, I'm going to start out with bus n being, let's make it low. So if we're in a system where nobody touches bus n at all, we're enabled. So we own bus n, so we're saying we're expecting it. We're expecting it to be 0 on entry, so we're expecting to be allowed to write something. If somebody wants to set it high, then they will attach to it and they will set it high. And we will see that high going edge and respond appropriately. There. Now, question is, oh, these guys need to be high. Is that correct? I'm going to scan forward in the document a little bit and see if anybody does anything interesting with bus enable. I don't think this document's going to have it. I don't want to start cracking up the MSI manuals or anything. Yeah, this is going to show anything. So I could either initialize it low and not worry about it, or I could initialize it high, and then the surrounding system would have to know to hook up bus n and set it high. I'll leave it low. That way, if we don't muck with it, it just works. Meanwhile, all of these guys are going to start high. So that statically initializes all of our stuff. Oh, except for status. CTL arrow status is equal to status reset. So we're going to set our status word to some defined value, and then we may adjust that value later on so that if somebody's wiggling bus n like crazy, we do something sane like not assert any outputs. Now, we're not going to do an invariant check here because our invariant is going to be, let's assure that we have all of the edges set. So let's write that down. So for data, our invariant is assert We want to assert that we have a pointer. We don't care what the content is. Any content there could be good. These guys are all edges. So we do edge in var of that guy. And of course, this needs change the left paren to CTL arrow. Okay, and status. Any status value we store is going to be okay as far as the invariants are concerned. It may very well be that we only have those 11 values that are valid, our reset value, plus the 10 values that the 8080 is supposed to send. It may also be that what I would want to do here is assert that certain combinations don't exist. For instance, if there's two signals from the 8080 that we should never see both of those status bits set at the same time. Maybe we'd check that. But for now, those won't change our invariants. Also, we could say as an invariant that we know that only one of these 5 signals is asserted. We could also say that if bus n is high, then we don't want to assert anything at all about them because somebody else might be wiggling them. Remember, even though we are the owner of those signals, the existence of bus n means that somebody else may take them from us, but we still own them. Okay, they would still connect up to our bus enables because they are not the guy that owns the control bus. We are. Okay, init, pop everybody high, status reset, linked. We come into the top of linked, I'm going to say I8228 invar CTL. So is there anything I would want to do based on imported values from these guys? Well, let's assert that they are in the state that we expect for the startup. What do I want to do here? Find the arrow. So, status strobe. When we power up, I believe the 8224 powers up with status strobe low. So we're going to assert it's low. We're going to assert that data bus in is not asserted. We're going to assert that write is not asserted, high. We're going to assert that HLDA is not asserted, and that's normally low. So when we are done linking the system together, it has to be in this initial condition, and that's the condition we want. And this location here is where we add the code that says, when this edge happens, call this function. But this is where I start writing my tests. So post. We're going to need an I8228 for power on self-test. Test start here marker. Kind of neat to have that because now I can say, well, how many lines of this file are above it? How many lines are below it? If we start getting awkward, I may move my tests out to separate files. I may even take all of the tests, move them out to separate directory. In some projects, I've gone so far as to have a directory of power on self-tests, a directory of built-in self-tests, and a directory of benchmarks. It means that when you look at a change request on a system, you can see very quickly what they're doing in the implementation, what they're doing in the testing, what they're doing in the benchmarking, and so on. So we are going to need a static I8228 called CTL, which is going to be used from here on down. I'm going to need a static function, which is going to initialize the whole thing. For testing, I am going to need these signals owned by the test environment. okay? Because we're going to need to attach those up to CTL. In fact, let's declare those first like that. Okay, so this is now telling us, oh, you never defined this, you never called these, you never used those. Fine. So this guy needs to do a I8228 init of CTL. And we're just going to use the macro version. It's going to call it CTL and do all the right things. And edge init of ststb underscore. Make it easy, dbin. We are underscore HLDA. Let's initialize the edges first. We're gonna build up the environment and then build up the things that are in it. Everything's low, but some things are high. That's high. Okay, so test init is defined, but it's never used. Well, this is going to be used to set us up for post, set us up for BIST, and then we're going to call it again. For benchmarking, we will have run the post, but I want to reinitialize before going into benchmarking because I don't know what state post will have left us in. Okay, so we are still golden. I'm going to put something down here to do basically a trivial benchmark. So what does the benchmarking code look like again? I always have to look this up. I will have to work out what our notion is, how much work we're doing during the call here that I'm going to make. This is a static function, static void, oops. Which takes a parameter which we are going to ignore. And then we go back up and we declare it. Okay. So we notice over here, a function that does nothing takes 1.1 nanoseconds to run in our environment. That's good to know. Which is one reason why we do a whole bunch of work inside this function. We divide by how much work we did, because the benchmarking overhead is non-zero. So what else do we do in init? Well, we have to say CTL, we have to hook up our input signals to CTL. CTL arrow, that is equal to that. Then we're going to go I8228 linked CTL. And now we have a problem. We didn't do a data. I'm going to make sure that the content of data is defined. Thank you. So what I'm going to do is I'm going to set this to status for the purposes of testing. What do I want to do? I'm going to set it to status fetch. No, I better set it to status reset, just in case. So when we write the test, we'll have to specify what the status is before we yank on status strobe. Okay, so yes, data with a capital D and the rest of it lowercase is a type. All uppercase is because the signal is called data, and I am using the domain language for that. Yes, I know, conventionally, all uppercase in C is a macro. But in this case, the language of the problem domain trumps any normal C conventions here. So, initialize all of this stuff, verify the data is correct. Actually, this is more kind of a that thing. We're going to initialize the CTL structure itself, and then we're going to connect up the things, and we're going to link it. And that's something that happens for post, BIST, and bench. Bear in mind, this is called in all three contexts, so we're not going to do anything that would be bad to do in one of them. Also notice that if we declared these up at the top, there's a good chance that the implementation code, when it was using a local variable, if I left something out, it would use the static instead, which would be a severe bug. This is probably the best argument right here for having the test be in a separate source file. We'll bear that in mind. Currently, if we put all of our tests in separate source files, we would now be overburdening ourselves with a huge number of very tiny files. When those files aren't so tiny, we'll do it. Okay, good to go. That means that as we implement parts of this system, we can also add code to the post. We can add code to the BIST to do more extensive testing, and we can add code to bench. So the next thing is, hey, why don't we implement some logic? So when we're done linking this, I am going to say edge. Okay, macro is edge on rise, edge on fall of CTL arrow STSTB underscore. Well, this is going to be interesting because we're going to be doing CTL this, CTL that, CTL the other. So let us pick up signals as necessary. I'm going to do it with these four first. Okay. So when status strobe falls, I'm going to call a function called on STSB. Let's call it latch sync in CTL. So I need a function called latch sync, which is going to go here. Static void latch sync of I8228 CTL. There we go. So now on the falling edge of status strobe, we will do this. And what I'm going to do is CTL arrow status equals star data. Now, what else are we doing when we latch that? If we looked at the timing diagram, I'm going to bop that up here real quick for a reminder. When status strobe goes low, we've got data on the data bus, and we want to drive these signals, whichever one is right, or we want to leave breadcrumbs so we can drive those signals later. Well, the breadcrumb we leave is the status signal. So now I need to go back to this table and figure out when I want to drive memread or IO read or int A. And turn that off. I think one of the reasons I have trouble with streaming sometimes is I will hit the stop streaming button instead of the button next to it, which turns off one of my windows. So bringing up in another window the Boolean operation that I figured out for this. Where'd it go? CTL 8228. Okay, so first of all, it turns out that memread goes low if the memr bit goes high, and this is high in the status word, and the HLTA is still low. So HLTA is a status bit. It's not HLDA. It's this bit right here. So the processor will assert HLTA when it's done a halt instruction. And that happens in this guy right here and this guy right here. Okay? And during those two, well, we don't have that. I better make a note in here about which control signal I'm going to assert just so I can have them all in one place. Where did my PDF reader go? Okay, there's the table, the lower bit. And I'm just going to copy that into here. So I'll just put it in square brackets. I'm going to need a bunch of space for it. I prefer to use the binaries up here, but I'm going to keep both versions up to date. Okay, so starting out with this, the table has instruction fetch at the bottom of this list. So this is memr, oops, slash memr, slash memr, MW. Notice how the writes are lining up with the WO going low in the status word. This is IOR, IOW, int A, int A. Okay. I'm going to do the same thing here. Let's see, can I write a macro to do this? I can write a macro to do this. And the closed brackets down below are going to be corrupted. We can fix that easily enough. Okay. So these are the signals I should be outputting here. Now, according to my other notes, we can say if, let's do a byte status equals like that. status amper status MR and so if memr is set and HLTA is not set, well, how does that work? Memr is set, memr is set, memr is set, memr is set, but HLTA is set. So that should work. Then we say edge low of memr, which means I also need these guys. Thank goodness for a good compiler. I believe the compiler will just remember that that's where we're getting them and it will do all the right things. No, let's use CTL arrow. Let's not write the code to be bad. So we're only going to do this, however, if CTL arrow bus n underscore arrow value is equal to 0. But this is going to be, the logic that's in here is the same logic I'm going to be doing when bus enable goes low. So I'm going to put another function up that says bus n fall. And actually, the internal logic might be better if I had just a support routine. So yeah, let's do two support routines. One for setting the read signals, one for setting the write signals. So static void update RCTL and sometimes I'll have status available, so I'll just pass it in there. Should I? No, I will not. Bus n fall is really just update RCTL. And update WCTL will happen on write control going low. Oh. But this has to be conditional on bus enable. Do I want to put the, yeah, let's put the conditional on bus enable here. Okay, so self-contained, update the read control signals. We're going to check bus enable. We're going to do the logic. During latch sync time, we do not update the write control signals. So bus enable conditionalizes both of those. So if bus enable is high, we don't do anything to those signals at all. I am actually going to set up functions for the other edges that aren't these update functions directly. I'm going to wash conditions back and forth for optimization later. Okay. So now if status and status, There's a signal called INP, bit called INP here, second from the left. We see it's only active in that particular input read cycle. Clever, huh? And input read is the only one that does IOR. So if INP is high, then edge low of CTL IOR. Oh, I forgot to set up all of these statics as for declarations. Okay, what else are we doing here? That's memory, that's IO read. Int acknowledge is asserted on these two signals. It lines up exactly with the int A, so we do something very similar here. Now for the right side, so update WCTL does two different things. When I'm going to use separate functions for it. Okay. So there is the update when when bus. Yeah. Okay. Let's write the logic first, and I can prune out inline and prune out later. WR rise says if. So we know we get here with WR. WR is low, therefore we say if CTL arrow status amper status out. So with WO, we get status out, so that's IOW, and we're going to get memW if we have stack. Well, if we have /O/WO low, then it's either memW, or IOW. So the logic in my other place was pretty questionable. But if let's take a look. If status out is set, we've got out. That's correct. So edge low of CTL arrow IOW underscore. Now, literally, if it's not this cycle and the CPU asserts the right signal, we can assume it's a memory write. So that actually is going to work. Okay. So what do we actually have here? I really want to grab these lines. Those are what I want to have for update controls. This is a byte status. Okay. WCTL again, byte status. Update WCTL happens on the right line and on the bus enable line, so we're going to write that differently. And again, I am working myself into a thing. DPN rise and fall. WR rise and fall. Fall and rise, actually. And we're going to need to have bus enable. So do we do anything relative to the rising edge of status strobe? And the answer to that is, checking this. No, there's nothing we need to do relative to rising edge of status strobe. There are some demands we make, for instance, that the CPU can't switch over to output data before the status strobe is done. But that's what we get. So now if I looked at the compile, we have all sorts of compile errors because I defined all these functions. Let's change latch sync to on STSTB fall. So I'm going to lay those out explicitly here. I think I'm going to move these update routines up above to give a better chance at inlining. I think that doesn't matter to the compiler now. That better not matter to the compiler. We will check that. I'll write it clear and then we'll check it. So STSTB's fall says gather status, latch it, and if bus enable is equal to 0, so if bus enable is low, then we can update our read control outputs. When the right signal falls, if bus enable is low, then we can say, well, there's two times where we would assert these signals. One is when bus enable is low and right it falls. The other time is when right is low and bus enable falls. Which means that these conditions are going to be checked inside the caller. Oh boy. This isn't just update, this is assert or activate. Don't want to use the word assert. There's assert and release, there's activate and release, and so on. Okay. And update RCTL now becomes that. WR rise, we're going to release WCTL. Now, one thing I could do is, as I set these, so when I set the signal low, in order to protect ourselves against certain kinds of asynchronous errors, I could at that time store the edge pointer to the edge that I asserted so that later on when I have these releases, I could just say, well, if that's set, then do it. That actually is a good idea. I'm going to have a piece of status here that says p edge asserted, not asserted, activated. So we're going to know what signal we activated, and we're going to deactivate it when appropriate. So the invariant is not going to check it. and it needs to set it to 0. And if we do one of these guys, we need to set activated to that edge. So there's a possibility you may attempt to activate more than one signal, but that would be an error in the status word, and we can check that. So I now only need a single release thing, which says p-edge activated equals that. If not activated, return edge high activated, and CTL arrow activated equals 0. I'm going to do it in that order, so if taking this edge high, if this action of setting this edge back high again causes, through a chain of effects, somebody to activate a different edge, we will not clear the one we activated later. So we're going to activate that like that. Now, if I was paranoid, I could do this. And all sorts of other things, but I think this is... I am going to use something that used to drive everybody crazy. Okay. Now we're going to do the same thing up here. This also assures that we only activate one edge. Oops. Okay, that can happen. If we get into here and we get a status value that's not one of the read guys, we're going to fall through that case. Now, the time to actually execute an assert is trivial given that we're fetching from there, so I'm going to be paranoid. More to the point, is it possible that this function needs to be idempotent? if we activate a signal with bus enable active, then we will activate the signal and it'll be inactivated. Somebody removes bus enable and we come through and in that process, we don't do anything, but the signal is still marked as activated. I think I can't do that. And I think that I need to do that too. I think I need to set the thing before I say if it's not, then return. This always sets it. Oh, can do that. Okay, back to the top. So status strobe, let's review. Says if bus enable is low, then we're going to activate the appropriate signal. Otherwise, we just leave bits and status. And if write goes low, then if bus enable is good, we activate the WCTLs. WR rise, we're going to release it. And we need similar for dBn. We do nothing on dBn rising, do we? We don't care about dBn rise, so this is just dBn fall. And on dBn fall, we say this die does not need status. So now we need to write the code for dBn for bus enable going high and low. So on bus enable rise, we are not going to do anything because we literally can't change the state of anything. So just bus enable low. We need to grab status. Activate. Now actually, I believe the optimizer is going to be fine for us. So on bus enable fall, we will grab the status word that's there and we will do the appropriate thing. And these need to be conditionalized. How? So we only set the read control if we're somewhere between when we strobed it and when dBn rose. So we need to know that we're after. So if we get dBn going high and then low, and then we get bus enable going, I don't want to change those signals. And for here, this is if CTL arrow WR underscore arrow value is equal to 0. So this tells me that when dBn falls, what I really want to do is set status back to reset. And when WCTL falls, I want to do the same thing. So once our, let me bring it up here. Oh, I still have it up. Okay. I didn't realize that. I've been working behind the thingy the whole time. So all that work that I've been doing has all been behind the PDF that I forgot to turn off. Let's review it real quick. Coming in here, inside linked, we're interested in falling edge of the status strobe. And as long as I've got the PDF up, let's use that for part of the comparison. The falling edge of the status strobe does stuff. And dBn Rising edge does nothing we care about. Falling edge does stuff. So there's that. And the right signal, falling edge and rising edge both do stuff. And bus enable, falling edge does something. Rising edge says don't do anything anymore. So there's that. So what do these do? One at a time. Status strobe falling edge says sample the data into the status byte. And actually I am going to do that. So we sample it into status. And if bus enable is low, then we activate our outputs. Activate our read controls. Bus N, we'll worry about bus N in a moment. When right falls, okay, down here, if bus enable is low, then we activate the write controls. Now, when write rises, we're going to release the controls, and dbin falls, we're going to release the controls. Now, when bus N falls, that says we may have had control signals we want to do. So we suddenly need to update them. So what we do there is we say if we have a status, so I'm going to muck with status later on. So this says when bus enable falls, we're going to assume that we are in this period here between when intake goes low and it goes high. So bus enable suddenly comes back. We're going to assert the signal. Boom. Probably a literal system would never do that. And if write is low, then we're going to do the other one. So here's our logic for activation, where we say activate read control says if we're going to do one of three signals, either memr, IOR, and int a, based on these booleans. And if it's none of them were done, if activated, edge low of activated. Let's just write it out like that. And if we're in activate WCTL, we say status out is set. It's either IOW or memW. And set it and do it. And release says if we're activated, then set to 0. What I'm also going to do here is CTL arrow status equal to status reset. So we're going to go back to our initial state and status, where if we do anything based on that status, it doesn't output anything. So what happens when we get into bus enable fall, we get activate RCTL, none of these are going to trigger because the status reset is everybody unasserted. Okay, so memr isn't asserted, input isn't asserted, int a isn't asserted, nobody's going to do anything. So if we clear status here, we do nothing there. And we would only, and if we bus enable fall after clearing and write is low, then we're going to do something. But if write is low and we're going to do something here. Oh, good. Bus enable is fraught. It is so tempting at this point to say ignore bus enable. Is it tempting enough for me to do it? It is. I'm going to apply a principle that we all knew back in the day called Yagni. You ain't going to need it. So we are going to not even have a bus enable edge. Add bus and later if and when we simulate a system that actually tells the A228 to not send out data on its control bus connections. And now we've got all sorts of compile errors. And all these statics are probably not actually defined anywhere. Let's go back up to the top and make sure we have them. So why is this? Oh, there it is. So activate WCTL doesn't actually need this. I think it's only called in that one place now. So we can start eliminating dead code. So WRIs and dBn fall are both just release. I would say release CTLs. Okay. Activate RCTL is only called in one place. Activate WCTL is only called in one place. And my indenter does weird things with this. So yeah, let's not use the ternary operator. I could actually do an else return there. Something similar here. Since there's only one guard condition, this actually looks a little bit clearer to me. Latch sync doesn't exist. activate RCTL, WCTL no longer exist. Release CTLs is in fact used right there. Oh, used but never defined. Okay, so are there better names for some of these? On STB fall, a better name is actually latch status, which I was using before. And on WR fall is start writes. So I want to name functions by what they do, not how they do it or under what conditions they do it. So now when I look at the code, I can say, well, goodness, when status strobe falls, we are latching status. When dbin falls, we are releasing controls. When WR falls, we are starting writes. And then we release controls when WR rises or dbin falls. That means that that logic is now a little more simple to describe. Some of these are still a little weird, but I think the complexity here is implied by the complexity of what's going on. And I've done it again. I'm editing behind the PDF. God damn it. Turn off the PDF. Rather than go back and show you things in the PDF, turn it off. There we go. Reviewing what I just said, now that you can see it. We've got the names clear up here describing what the functions do, not how they do it and not when they're called. So inside link now we say that on falling edge of status strobe latch status, on falling edge of write start writes, on falling edge of data bus in release the controls, and on rising edge of write release the controls. Latch status is a little complicated, but we're reading the data and storing it. We are deciding which signal we're going to activate or none. We're logging it and we're activating it. We log it before we activate it in case the act of latching that edge does other things. Start writes is we decide which of the two signals we're going to do because we know we're going to do one of them. We wouldn't have a WR signal from the CPU unless it was one of these. Release control says whichever signal we activated, we're going to release. Which means if we're writing and somebody asserts and releases dbin, it's going to release it. But that's an error. If we're reading and somebody asserts WR and releases it, and then that's going to release this too. Now there's a potential thing. Reading and writing at the same time. Okay. There are tricks you can pull. I have done this, where you can design your circuitry to read and write. So read from a ROM and write to a RAM at the same address. It makes for a very fast copy of data from ROM to RAM, which happens only precisely one time, which is when you're powering up, and it probably completes before you got your hands off of the power up button anyway. So it's an absolutely unnecessary optimization, but it's kind of cool to design it and use it. It's fun to get it working. And then once you've got it working, yeah. I'm going to not talk about bus enable at all anymore because it turned into just extra stuff, and I don't think we're going to need it in at least the first system we implement. Because bus enable is a DMA thing, and I'm thinking that what I will do is I will route my special devices, my simulated devices. I'm not going to simulate the actual chips of a disk controller. What I'm going to do is I'm going to have a simulated disk where when you say read, it's going to magically appear in memory a certain amount of time later. Not go over the bus. So. How are we doing for time? 4:10 p.m. Okay. This should cause all the signals to move properly. And now what I want to do is write a power on self test that cycles through things, presenting each of these status words and assuring that as the signals move around in a normal cycle, in the order they would move in a normal cycle, that the right consequences occur. Now, I'm going to end up with a subroutine for run a cycle at some point, but let's write it out straight. Get the two header files involved in the same area. And I have the table here. So with status set to status reset, which is the initial value, I should be able to see that all of these signals are high. Let's say only one of, let me say, which signal is going to be low here? Check outputs. I'm going to say all of them are high, so I'm going to pass in a null pointer. And this gets moved down later. So we wanted to look through each one of these signals. If it's equal to E, we're going to say it's low, otherwise it's going to be high. Write out the logic directly before I start optimizing. For each one of these signals, we're going to do something with a keyboard macro. Find the semicolon. Find the space. There it is. We're going to say p edge foo equals ctl arrow foo. Now, if E is equal to foo, assert EQ integer 0 CTL arrow foo arrow value. Okay. Now, how can I make this smaller? That's best. I want to do it in post. So we're going to get it running in post, and then we're going to copy it down to BIST. And then we're going to do the normal thing where we make post smaller while making BIST bigger. So all of these asserts can now have the same thing done. I can take this. No, let's leave them like this. So when the error output happens, it will point me to the right one. It will say 0 or 1 instead of E equals memr. So I will be able to tell from the error output which one I was looking for. Okay, so now we're going to step through our status bytes one at a time and verify when we cycle through the appropriate control signals for that status word that it sets these signals at the right time. So star data is equal to status fetch. So now we say, well, we need a lowering edge on STSTB, so edge low STSTB underscore. And we know that immediately I'm going to actually need these edges available without saying CTL all over the place. Let's do that. So immediately with the status strobe low on a status fetch, we should be seeing memr. Unused, and we have a test condition failed right there. Okay. This is saying that I am requesting memr. This has gone low. We did an edge low status strobe. It should have done everything, and it didn't. Okay, so we have a test failure. Our first test, the first condition of the first test says E equals memr, and it's not 0. Oh, the other thing is I don't need CTL in front of these. So now we debug it. First of all, did we get to linked? Let's make absolutely sure here. Stub 8228 linked and ready. Yep, we're getting there. I'm going to print out the status in octal because this is an 8080. We're not getting into latch status, which means STSTB was already low when we started. I should have remembered this. So when we start, we're on power on reset. So come out of reset. Okay, thanks. And we should still have no outputs here. Oh, and I almost forgot. We need to, as we step through this, I have to bump tau each time, don't I? Okay, so now we are properly latching that status here. So I know we're getting into latch status. And oh, the rest of this is working too. I think what I'm going to do is put this out here in the middle in case we want to increment tau by more than that. And I'm going to make it really clear where time is stepping forward. So come out of reset, we set that high, check outputs at time 0, step to time 1 where we set data and drive the status strobe low, and we check that memr is now set. time 1, we set that high. MEMR should still be set. I'm going to keep the timing diagram up on my right so I can see it, but I'm not going to put it on the screen because I keep putting things in front of my program text. So status strobe typically only lasts for 1 tau. If I was simulating the system with other timer requirements, I would do something other than tau plus me minus 1 plus equals 1, but we aren't. So MEMR should stay high as we edge high dB in. And then when it goes back low again, 0. So this whole sequence here from status fetch down through the end, we need to repeat this for each data byte. So check outputs, I'm going to do a check read case read. And I'm going to pass in the status word. And the edge that I'm checking, and this is a read case, which means it's a dB in thing, which means we're going to grab this whole thing and put it in here. Like that. And now this becomes check case RD status fetch MEMR. And let's increment tau at the top of this case rather than at the bottom. And that gives us a problem here because passing argument 1 of check case read makes pointer from integer without a cast because I put, status fetch here. Well, I do need to have an edge, don't I? And a status, and they do need to be in the right order. The edge is MEMR, and the status word is status fetch. Everywhere else I put the edge first. Edge status, yep. So we still have an assertion that somebody is being changed with their tau wrong. Is it there? Yeah. I could have popped open the debugger for this. Okay. As the comparison here is that we are running post. So this is now a function that we can use to test the status signals that are allowed until dB in. And this is going to be the case without HLDA. So I want another case that is with HLDA. So in the presence of HLDA, that means HLDA is going to go up while dBn is high, and I'm going to see it go low. So this is going to be edge high of HLDA, and it's going to go out like that. And we need to restore HLDA before the next test. This also means we need to assure that HLDA is 0 when we start. Independent of what the power on conditions are, our test requires for proper functioning that these guys are starting out in the 0 state. Okay. So now somebody is not releasing memr when they should be. Well, let's run the debugger on this one. So this is check case read HLDA line 232 right here. So when HLDA goes high, we are not releasing memr. Well, that's because I forgot to put it in. So when HLDA goes high, we're going to release our controls. And this says nothing at all about a descending edge on HLDA fixing things up. So I'm going to assume that that's okay, that people know that when HLDA goes low again, we're not going to get these control bytes back. Okay, so we are back to basically working again. And of course, I haven't used any of these edges. So start working our way down the status byte values. Fetch mread is next. And that just works. Now, mwrite is going to be case WR. WR doesn't have HLDA stuff. So for the write case, you do this, but instead of high dBn, low dBn, we're going to do low of WR underscore, then high of WR underscore. So I think I forgot to declare this. Yep. Okay. So test condition failed here. Because I am not using a big ol' honkin' testing framework, I don't really know what this did, but I do know it's what I just changed. And that's because I didn't put the right signal name in here. So this is saying test condition failed here. So memw is supposed to be 0, and it isn't. And we are at check case WR259. That's here. So we strobe STSTB. Because for WR, we don't activate it yet. So that's the correct sequence for the right signals. And now we're working again. So status fetch, status read, status mWrite. We have sRead and sWrite, which I can just do this. And we've added more test cases. Bada boom, bada bing. We have input read and output write. Input RD. And these are going to do mem becomes IO. How about that? These are coming together. Since I got the correct logic in the check case functions, all these tests are just coming together very nicely. Intact, haltac, and intact W. Intact and intact W are read-like things. Which do, instead of memr, they do INTA. And then we have one that does nothing. Haltac. It's my understanding that Haltac, you don't have any dBin signals or any write signals at all. So this is really a check case. Oops. Nil. So we're going to pick this up, but we're going to say that dBin doesn't occur. And check nil means we get no outputs. And I'm going to explicitly do a check case nil, not only of this one, but also of the reset value. So what are the differences here? Status reset is 2. Oh, check case nil probably has an edge. Yeah. And that works. And if I wasn't printing out the top and bottom of my post function, the comparison would probably be correct too. Indeed, it is. So power on self-test now checks to make sure that each one of these signals is doing the right thing. Okay, and we're going to take our support functions and move them down to the bottom where they belong. So the next question is, do I want to do anything at all in BIST? Well, BIST doesn't depend on post running. Let's copy it. Maybe BIST will just duplicate post. Okay, I think I will probably add something inside BIST to print things as we go, but not today, not right now. And for benchmarking, I don't believe that there's any meaningful benchmarking we can do at all here. But I will leave the framework in place in case I figure out there is something. The question is, how long does it take for me to turn around these things? And that mainly is more an artifact of the Edge package than of this package. So I don't think there's a meaningful benchmark for the 8228. And with that said, I think we are done here. I think this is actually a working 8228. I am going to close the stream. I'm going to add some comments to the code and touch it up a little bit and add some more, add another paragraph to the README. Notice that's up there. I have a line for this. I need to add a line for that. I need to put in some comments. I need to touch things up a little bit so that they are pretty and they are aesthetically what I want. And then that will go up to GitHub. Aside from that, I think now is the time for me to switch my attention over to thinking about computer games and perhaps about supper. And I will see you all in the next one. So keep it safe and keep it fast. Talk to you soon.